Good evening. It was awesome to see so many of you at the Friends of Medicine seminar series. My wife in the back, Dr. Weinkoff, presented along with Dr. Chris Hopkinson. So we had pretty good turnout, I think 35 to 40 people. Had some good questions afterwards about how do you guys get involved and what can you do. We have 3 more of these talks the rest of the semester. They're the next 3 Wednesdays, 4 to 5:30 in this room. So check it out, Friends of Medicine. If you go to UALR Friends of Medicine, Google that, you'll be able to find the website, the descriptions, and hopefully find something you're interested in. We're going to start off class today just diving right in. If you haven't got your exam back, the short answers back from me, then at some point today I'll try to hand them out to you in class. I have those graded. And overall, I was pretty happy. Our average went up about 10 percentage points from exam 1. So good job, guys. I think you're starting to figure things out or figure me out. If your score's not where you want, then try to make a point to either come to office hours or find a group of people that can find an alternate office hour time that would work for you guys if you can't come to my regular office hours. And let's talk about how to make your exam scores and your assessment line up with what you know you're capable of. I'm not going to do an exam wrapper for exam 2. As you can tell, I don't even have time to finish grading exam 1's exam wrapper. I'm still working on it. It takes a long time to go through and try to see what you guys are thinking about for exam questions when you redo them. So for now, let's go ahead and work through this question. Spend a couple minutes, try to think about what it's asking, what information you have, how to set it up, and then we'll work through it together. So please, if you get stuck, we have multiple people to help here, so raise your hand and we'll kind of move around and help you out.
What we're doing now?
Only thing I can think of is just like concentration and assume that it's
what's it called? Where you have to take a double take worthy? I'm not. The silence says it's fine.
I mean, I think that's what every
But in moderation, so what I did is I took it.
All right, let's bring it together to make sure we're all working on the same trajectory. This is an equilibrium problem. How do we know that? We're given an equilibrium constant. Okay? If you're given an equilibrium constant, it tells us there must be a reaction. And then if there's a reaction, we should be able to write it out. So have you guys written out the chemical reaction already? Okay, so take a second, write out the chemical reaction. What's happening? There's some hints in the wording of the question for what type of chemical reaction that is. All right, so can I get someone to volunteer with the equation? Once we have the equation, I can kind of let you guys go, but we need that equation first. What's the chemical reaction? Who can help out? Snider. Say again? And what state would that be in? Okay, so almost. So what do we have slightly tweaked about this? It's a pretty important tweak, but it's just a slight tweak. We'll get it there. Flip it around. All right, so the idea is if we have solid iron 2 hydroxide, how do we know it's FeOH2? Hydroxide is -1, formal charge. Iron, the Roman numeral tells us what the formal charge is, positive on that iron. So Fe2 plus with the OH minus, there's two of those. How much of this will dissolve in water? That's the first question. And so that's something we did at the end of last class. We didn't actually calculate it. And now I'm asking one harder question. So we kind of leapfrog because we didn't get that answer last time. But I want to know how much of this is going to dissolve if we put it into a solution that has what we call a common ion. Why does this have a common ion? Why does that term make sense? Love?
Because that compound with dissociation with 2Fe2 plus and solution, it's a solution of Fe2 plus.
It's going to generate Fe2 plus, so one of the ions that it already disassociates into, it has in common with what's already dissolved. So we need to look at this as, here's it written out the appropriate way when we flipped it around. How much of this iron hydroxide solid is going to be able to disassociate in water? And it's going to generate 2 hydroxides for every 1 iron 2 plus if we start with some iron 2 plus already in solution. So how do we answer this question? What's the approach? Let's talk really big picture. Let's write out the equilibrium expression. So go ahead and do that if you haven't already. What do we call this particular equilibrium constant? Solubility product, KSP. All right, and then who can tell me what that equals? Go ahead, Humphrey. What are we missing? What's really important in the wording of that? Say again? The concentration of. And we could write it over 1 if we want. Why do we not include the concentration of iron hydroxide? It's a solid. There can be an infinite amount there, and it doesn't determine how much is dissolved. What determines how much is dissolved is the solubility product. All right? So what we're asking is, what is the molar concentration of iron 2 hydroxide that can dissolve, if we already start with something there? So big picture then, what do we do next? We have our KSP. We know that that is that very soluble, not very soluble? 10 to the negative 17. That means that the concentration of this times the concentration of this squared. Do you think these are 1 molar each when it goes to dissolve as much as it wants? It's like 0.000002 molar maybe, and same here. And we square that and we get 10 to the negative 17. So this is a really, really small concentration. So keep that in mind. And then how do we actually solve for this? What's the big next step? What's that? Let's do a nice table. Think about what your initial concentration of each is. Think about what your change is. think about what your equilibrium is, and then how that relates to molar solubility. So go ahead and work through this. I'll give you guys another couple minutes to write it out as an ice table. Keep in mind your stoichiometric coefficients, keep in mind your KSP, and try to figure out what that molar solubility is.
Because, yeah, that's the thing, because initially you had that, but you have your right, you had 0.
And it's irrelevant in the terms of
Hold up, but we know what this is. We know what
That's why we wrote our KSP without concentration. Once you start with 0. All right, so let's go ahead and work through this a little bit together. When we're doing KSP, a lot of people are trying to put concentrations here, but remember this is a solid. We're not talking about the concentration of the solid. We'll answer this question about the molar solubility of that salt at the end once we know how much of the parts dissolved. So we're not even putting anything on the left side. But on the right side, what are we going to put for these two initial concentrations? Josh?
4.0 times 10 to the negative 2 and 0.
Because we start with some of the common ion already in solution. We don't have any hydroxide in solution. So what we're saying, you need a hand? Do I have those? Are they in my office? Alright, next time we start working, I'll give you figure it out. So if we have some of this iron here, do you think that's going to help dissolve the iron hydroxide? Or do you think it's going to make it more difficult for iron hydroxide to dissolve? It's going to be more difficult because it barely goes into solution as is, and we already have some there to start with. It's going to make that process more difficult. So what are we going to do for our S's here, or X's, whatever letter you guys want to use? Is it going to be a minus X or plus X on the right side of the equation? Plus. Why? Because some is being produced. Okay, why do we know that that's the case? Give me some reasons related to equilibrium. Kalia.
The K is less than 1.
K is less than 1, but that doesn't really get us where we're going. Maybe the right track. What is Q right now? What is our initial Q? 0 squared times something is 0. So our Q is 0. We're slammed all the way over on the left side of this reaction. That's one way to look at it. So Q is less than K. The second reason is we don't have anything here, so we can't consume this to make that. All right? So then we have just plus X and plus X, right? All right, so we consider our stoichiometric ratio. And then our equilibrium is going to be based off of that change. All right? So can you solve for S now? What did I do? Talk to your neighbor. What did I just do, and is it legit? Is it okay to do? How can we estimate whether that's okay or not? All right, so why did I do that, and is it okay? Can I hear Tyler, Lynn, Maggie, your guys' group's thoughts?
Confused. I'm confused. I feel like I got lost as to, like, I would have thought that it would be the 4 times 10 to the negative 2 plus S squared, not squared, times, yeah.
Times 2S squared.
2S squared, yeah.
Okay, so that's right here. And then I said, but that's about equal to this.
Okay.
So that's the question I have. Is this okay to do, and what did I do? Carol?
Isn't that 5% thing that you're saying?
So it's related to 5%, yes. So what's the gist of that, though? Avery?
You're basically saying that that S is so minimal that it wouldn't really factor in, so you're just going to take it out.
So we just said a second ago that 10 to the negative 7th means that this stuff dissolves hardly at all, right? That we expect the solubility, if we had nothing in there to start with, to be, I don't know, 10 to the negative 5th or something like that for molarity. So we just do some mental math and say what times what squared is going to give you 10 to the negative 17th, maybe negative 5th, right? Negative 5 times negative 5 times negative 5 is negative 15th. Somewhere in that ballpark. So is 10 to the negative 5th significantly greater than however much is going to come off of that solid chunk? That's what we're asking. 10 to the negative 5th would be what I'd approximate this to be. That's 1,000 times bigger, or 1,000 times less than how much we have in there. If you're ever not sure, try. But if you try, you have to come back and test it afterwards, okay? So we'll come back to that in a second. So our approximation was that this amount that dissolves is going to be insignificant coming from iron hydroxide as opposed to what's already there. So we're going to say, well, that's about how much we started with. And if we do that, can you guys solve for S? You guys see where I got that number? Yeah. This is 0.04. This is 2 squared. So make sure you do order of operations right, or else you'll get this wrong. Can we now solve for S? Go ahead and solve for S real quick. This is where you test your calculator skills and your algebra skills. You guys get about 1.74 times 10 to the negative 8 molar. I know that you guys don't love doing mental math. A lot of people don't. I always advise doing mental math before to get an idea of what your order of magnitude should be. That's what your exponent should be. If you don't have any idea what your exponent is, then any number is going to just look fine. Yeah?
Can you explain how you got the 16?
The 0.16?
Yes.
So this is 0.04. This is 2 squared. So 4 times 0.04 is 0.16. So just doing order of operations, 2s squared is 4s squared. You got rid of the parenthesis. Multiply this by 4s squared. All right, so what is that number? What does that tell us? What do we do with that number now? Talk to your neighbor. What do we do with that number now? How do we answer this question? And what steps do we have to do? Talk to your neighbor real quick. Figure out the next step. All right. So let's do a couple questions, and I'm going to come back to something that Josh just brought up. What is the S, and then how do we use that to answer this question? Moed?
So, what my sources have been telling me is that that S is actually the same factor that it's like pushing the reaction forward. So technically, iron 2 hydroxide should also be S. Unless my sources are wrong.
Might have been oversimplified a little bit. So let's, before we go that far, what is S? What did we just calculate? Tripty?
Is it the change in the system?
Okay, be more specific. Change in, you can do a couple of specific things there.
Like 4 from 0 to the negative 2 plus S. It's the change from the initial concentration to the equilibrium plus.
Great. So that is the amount of iron hydroxide that dissolved. It is the concentration of it that dissolved that added to the amount of iron 2 plus that was there. What's another thing you can refer to that S by? What else is that S? Colin?
Solubility.
Okay, and we're going to get there in 1 second, how we actually state that. But the other thing I just wanted to have you guys think about is that 2 times that S is our final concentration of hydroxide. or the change in the concentration of a hydroxide. So I'm going to go back to a question that Josh asked me over the side. He said that some people aren't understanding why we decided 0 was our initial concentration of one of the two things. Why is that? Clear?
Because we're talking about common ions, so it's starting out with some of the Fe2 plus already in the solution, so we would have some problem. I guess the system is modeling some issues we would have forcing the FeOH to dissolve into the solution.
Great. So this might be, a geological example of this might be that you have a water source that already has other minerals that are dissolved in it. Or it might be specifically that you are working in tap water that has iron nitrate already dissolved in it. Nitrate is irrelevant for the solubility of iron hydroxide. But what we're saying is that through another compound that's in there, we have a source of iron 2+. That iron 2+ is going to influence how much of the thing that we want to dissolve can actually dissolve. So if we want the iron hydroxide to dissolve, there's nothing pushing back on it from the hydroxide side, but there's something pushing back on it from the iron side. So if one of those ions is already there, it's already taking up that space in the water, and it's going to drive that reaction to the left a bit more. It's going to make it so that the amount that can actually dissolve, going back to what Colin said, S in this case is our molar solubility because it is a 1-to-1 stoichiometric ratio. So we're going to say that the molar solubility is a stoichiometric coefficient of 1 to what we start with. So it's basically saying, what's the molar concentration of iron hydroxide that dissolved? That's what molar solubility is. And we can influence that by adding a common ion or being in a solution that already has a common ion. So in this case, we only have one of the two ions in solution. We don't have the other. The other is going to help draw it into solution. Question? Thoughts? Calculation-wise, are we done? What did we forget? So if the question asked, what is the concentration of hydroxide at equilibrium of this solution, we would have to multiply it by 2. Because we're asking the molar solubility of iron hydroxide, we don't have to. S is our molar solubility of iron hydroxide. What step did we skip, though, Christina?
We didn't make this less than 5%.
This approximation, we didn't check that. Go ahead and check it. Do you need to do a calculator to check this? So if this exponent was close to 10 to the negative 2, if it was 10 to the negative 3, we might want to check this. This is 10 to the negative 8 versus 10 to the negative 2. So what we're saying is that this concentration is really not increased at all by the amount that dissolves from iron hydroxide, iron 2 hydroxide. So the approximation was valid. We can do a percentage, but it's going to be like 0.0001% or something like that. Yeah. 10 to the 6th, literally a million times smaller. All right. So I kind of gave you guys a really, really hard solubility question up front. This is what I want you to be able to do. I want you to be able to look at a solubility question, use KSP, and not always assume that our initial concentration is 0. How does that factor in? How big is that compared to what everything else is going into the equation? Questions? You guys seem really comfortable with this. I'll put together a practice problem set for this weekend. That'll have some more KSP problems, so you can go ahead and work those if you want some more practice. So these could also be alternate versions of the question. What is the concentration of iron 2+ at equilibrium? What is the concentration of hydroxide at equilibrium? What's wrong about this one? Concentration of iron 2+ at equilibrium. Is that what it actually is? What is that number?
It will be plus 4.0 times 10 to the negative.
This is the amount that came from iron 2 hydroxide. And so this is plus, if we want the actual concentration in the end, it's going to be adding those two together.
Dr. Bailey?
Yes?
If you were asking that question on a test like what is it at equilibrium, you would want us to add it together, wouldn't you?
So the molar solubility is going to be, in this case, S. Wait.
If you were to ask us like what the concentration was of the Fe2+,
Yeah.
you would want us to add it together, right? You wouldn't just want that difference value?
Correct.
Okay.
Colin?
But if the difference is like more than 1 million times, then with significant figures, that 4.0 times 10 to the negative 2 is not going to change.
So you could do some great mental math at the beginning of this question if it was an exam question like this, and just say, it's not going to change. Done. Full credit. So if you can do that mental estimation and comparison, it could save you a lot of time. All right. Learning objectives for today. I want you guys to be able to calculate how molar solubility can change if there's a common ion in solution. I'm also going to want you to be able to calculate the pH of a solution if you know the Ka or Kb and concentration of the acid or base. And then we're going to do some comparisons of the relative strength of acids and bases. Hopefully if you guys got a chance to work on the activity, 42, it gives you some insight into what an acid is, and then 43 started on the strength of it. Finishing out that packet is going to be hugely valuable. We're not going to have time to do it in class, but to turn in for today, well, tomorrow, because I pushed it back, for those who did come to, I should have been like, if you come to the talk, then you can turn it in tomorrow. That's what I should have said. Wording. And then we're going to talk about relative strength of acids and bases and how that relates to Kw, which is what the activity 43 did go into to some depth. So I'm not going to go into that too hard because I do expect you guys to work on that as well. And then the last thing is if we have pH or POH or concentration of H plus or concentration of hydroxide, I want you guys to understand how those relate to each other. There are some other really good POGL activities that we will not work through. 43, we've only done Model 1, so finishing the rest of that is going to be very helpful. Activity 45 is going back to that idea of what is a log and how do we use it and what is pH good for with the PHOR. It's kind of cute. And then activity 46 starts to look at the molecular structure. Why is something more acidic than something else? We'll talk about that a bit in class, but this really helps kind of nail it down. So if you're looking for study material, these are fantastic. All right, so let's see how you guys, let's not do that, let's see how you guys do on finding the pH of a weak acid in solution. And let me know if there's an additional piece of information you guys might want. All right, you guys have it. All right, please raise your hand if you need help getting moving or get stuck. So H plus, H3O plus, To get to what it should be. Steps. Because you're gonna
What's up, Yo.
I'm just assuming you didn't.
I didn't look up, I just went up there.
Yeah.
That much.
There's only
you know that K is not one.
this line right here. We're about to focus.
I don't know if he's right.
I'm pretty sure he's not in.
You know, I do know. I don't think you are.
I don't think you know yourself that well.
Which segment? Which segment? We did a lot of this one.
All right, let's talk through our steps. I think most people have gotten a chance to kind of go down one or two dead ends. And then, biggest misconception or biggest pitfall to go into. Let's take the negative log of the concentration of the weak acid. Did anyone do that?
Oh, yeah.
No? Nobody. Okay, that's good. You guys are better off than most. What's the problem with that? All right, so we're saying that this acid, we're describing an acid, and acid is something that, in our definition, gives up an H plus ion. Right, so we have a carboxylic acid, CO2H, that this H is going to separate and be released. How do we know that doesn't happen completely? What information do we have that tells us that? There's two major pieces of information we can't ignore. Josh?
There's still an H in the other side.
Oh, well, there's other... That's a typo.
Okay.
Fail.
So I just passed it here.
All right, so some bumbling idiot, myself, left an H on the product side.
Very confusing.
That's crazy. That's a really bad mistake. Okay, so without that H there, how do we know that every single acetic acid doesn't end up as acetate and H+? There's two really major ways that we should be able to tell that doesn't happen. Matt?
Well, when you see the equation written, the arrow is saying that the reaction is going in both directions.
Great, so there's an equilibrium arrow. It tells us the reaction is going in both directions. So that's part of it, and that's actually 2.5 really obvious things. So that's a half because that might be used generically, but if it's used appropriately, you're right. Look. Okay, so going to what Matt said, if it is an equilibrium that goes in both directions, we need to look at the K. What K value would you expect if it goes all the products? Greater than 1 and much, much, much greater than 1. Is our K value greater than 1 or much, much greater than 1? So we look at that K and we say, well, there's a higher concentration of reactants than products, 10 to the negative fifth. All right, so right then and there, we should be able to say that this reaction does not precede all to reactants, and in fact probably precedes a very small amount of products. Precedes a very small amount of products. What's the second way? It's much more intuitive, not numeric. What do you call something that goes all the way to the right side if it's an acid? What's that? I can't hear you, Todd. Or Humphrey. Strong acid. All right, one of the things you have to memorize this semester is a strong acid. There's tons of them. No, there's only 6. All right, hydrochloric, hydrobromic, hydroiodic, nitric acid, sulfuric acid, and perchloric acid. There's only 6. And if you don't see one of those 6, then you're safe to say that there is no way the concentration that you put into solution of this is going to all end up over here. In fact, most of it won't. So those are 2 ways you need to make sure that you don't fall in that trap. All right, so if not all of it dissociates, how do we figure out how much? We want to take the negative log of the concentration of H+. I totally agree. But what is the H+ ion concentration? How do we find that? Ice table. The other word for that is percent ionization. So you guys had that in activity 43, is that right? So find what the percent ionization is. Find out what that value of X is and look at that as a percentage of the initial. So go ahead and set up an ice table. Figure out what that pH is. Figure out if you can do the assumption. But then we check that. So is this your initial change?
These are not
What's your initial concentration of?
Because you have to be able to get those 2 sig figs out. So when you do 10 to the negative whatever, you have to do 2 sig figs that way. So you have to have those numbers to get to.
okay.
These are the added. That is the yeah.
It's 1880, so it's squared K here. And plus B, which is are you smart? It's just the he wants us to be like squared.
So the reactions of either of these are together. Here's the
It's not always signs.
All right, we have 21 responses. Is this a pretty challenging topic? The crazy thing is, in like a week or two, you'll be like, oh, this is like super easy, I got it now, once you figure out how everything fits together. So don't stress too much if this is hurting your brain. Hopefully the supplemental activities will help conceptually get you there. And then in class, we're going to really work on these ice tables and how to use them. So we're going to make our ice table, rice table, whatever you want to call it, put the reaction at the top. Do we know our initial concentration of our acid? What's our initial concentration of the acid? 1.25 molar. And do we have any H+ ions in water when we start?
No.
Tyler, what is that little? So we actually do. We'll talk about in a second about autoionization of water and how water all times. What's neutral water? What's the pH of neutral water? 7, which means the concentration of H plus ions in neutral water is pH equals 7, so 10 to the negative pH is the concentration of H plus ions. So 10 to the negative 7th molar is the concentration of hydroxide or H plus ions in water at all times, at neutral water. Okay, we call that 0. 10 to the negative 7th molar, that's really, really, really dilute. So we're going to say 0 and 0. We're going to come back to that, though, and that assumption is not always valid. All right. So are we going to have minus x plus x on the left side of this reaction and y? Minus or plus? Minus or plus? Why minus? Great, so 2 different ways. I love it. So 1, there's no products, so we can't use those products and combine them to make reactants. It's impossible. The second way is what Kalia said, and that our K value is greater than 0. So we start out with Q equals 0. We have to take all reactants and make some mixture of products and reactants. So there has to be some value here in the end. So we're going to use acetic acid. That's going to break apart. Every 1 acetic acid is going to give you 1 H plus ion and 1 acetate ion. It's really killing me that there's an H in there. All right. So then at equilibrium, we have our 3 concentrations. Can you solve for x now? Can we make our lives easier? How do we make our lives easier? Let's do an approximation. What are we approximating? Are we approximating that this x is 0? No. This x is 0? All right, so we have to be really careful at which of the x's we're making the approximation for. Because our concentration is relatively high, we know that 10 to the negative 5th is the Ka value, so that's a somewhat small k. So we're going to say that it's not really going to change much. It's going to be about 1.25 molar in the end. A little bit, but it's going to dissociate. So then we can find x squared, and we can find our x. Done! All right, so turn to your neighbor and tell them the 2 things that you can say x is. There's actually more than 2. What is x? If you were to turn to a friend and say, what is x? And have a correct statement, what would you put in that sentence? All right, can I hear from David or Marlene? What is one thing you could say that x is? Yeah, and even maybe more specific than that, which way did it change? Okay, so that is the decrease in the concentration of our initial acid. All right, great. What's another thing you could say x is? Bria? Bree, sorry.
I misunderstood the question initially. I thought you meant numerically. Because there was 2 x's when you solved the quadratic.
Oh, I didn't use a quadratic.
Yeah.
We approximated.
You approximate. I used a quadratic because it was a mess. And
Yep. That's why on an exam I will never give you a quadratic. Somebody has to solve a quadratic. If I made a huge mistake and you did have to use a quadratic, then you would just say right there, you would write out, you have to use quadratic to answer this, I'm done. And then I'd give you full credit if it's my mistake. All right? So what else does x mean? Matt?
The concentration of hydronium ions.
Great. So the concentration of H3O plus at equilibrium, and you'll notice that chemists get lazy, and we say, well, it's in water, it's aqueous H plus. It's the same thing as H3O plus. So hydronium is actually more accurate than proton concentration. We use them interchangeably. David?
So we can make the assumption that you're going to use the assumption.
Yes. But you have to show me that you check to show that it's valid.
Okay.
We'll get there in 1 second. All right? What's one other thing we can say that x is?
Molar solubility.
It's not molar solubility because it's not a solid dissolving. Let's try that. What's one other thing it is? What else is X, the concentration of at equilibrium? It's our concentration of acetate at equilibrium. So I could ask you any of those questions. What is the change in concentration of the initial acid to get to equilibrium? That's X. What is the concentration of H plus ions at equilibrium? That's X. What is the concentration of acetate at equilibrium? That's X. All right? All those different ways to do it. So then how do we actually find the pH? The reason it's so important to actually say what X is that a lot of students will just get X, take the negative log, and be done. And that is not always going to work. There's a lot of times where that will not work because I will give you information that needs you to go one step further. So Austin, what is the last step we need to do now?
We're going to take the negative log.
So if we just take the negative log, what did we forget to do? What is one thing we have to do, David?
Prove our assumption.
Prove our assumption. Is this less than 5% of the initial concentration? Did anyone do the percentage? What is it?
Or 0.376, not the zero. The zero was before.
I verified.
I did not type it out here. Okay. It is less than 5% by a significant amount. So once we verified that the assumption was right, then we can do the negative log of the concentration. And is that 2 sig figs or is that 3 sig figs? So you pass the decimal. That tells you about 10 to the negative second molar, right? And then 2 sig figs. All right, how do you guys feel about that?
So how do we check it again? Like which number do we just do?
So we said, is that less than 5%? Because that's the assumption we made. Does it change it less than 5%? So you can do whatever math you want, do whatever comparison, as long as you show me that's less than 5%. You can subtract it and show that that's more than 95% of the original number, or whatever you want to do. All right. How many of you guys got there and feel confident in that? All right, plenty more opportunities to work through ice tables. But this is something that you really need to get comfortable doing. So let's think about what a Ka value is and what it tells us. So let's think about benzoic acid. Which of these Ka values would you guess to be appropriate? Talk to your neighbor. Go ahead and check. All right, about to close out. We can answer. All right, can I hear from a new voice? How did you guys choose which one? New voice. New voice.
Weak acid
Lindsay?
versus strong acids.
Great. So, how did you use those terms to decide which one of these you'd answer?
I know that that is a weak acid, and so it will not completely dissociate, so the reactants will be greater in the product.
Fantastic. The reactants will be favored. And the majority of the class agreed with you. So our K value tells us, is this product favored? Is it about an equal mixture, or is it reactant favored? A weak acid, you're going to have a couple telltale signs. The most important one is if you memorize what the strong acids are, and it's not on that list, you're done. The other way is carboxylic acids are always weak acids. They will always have a K value, a Ka less than 1, which means that they're reactant favored. Now you can change how acidic that proton is, how likely it is to be released, by tweaking the rest of the molecule and what it's attached to, you can actually change that a lot, but it's never going to be a strong acid. So what I want you to think about is a generic version of this reaction. So we're going to talk about our definition of an acid is it releases something that releases an H plus ion. If we're going to do that, sometimes we don't need to have a specific example to show that. I want to have a generic version of that to describe that dissociation. So we're going to use a generic version written out like this, a decent amount in this class. So how does this represent an acid on the left side? Matt?
It's an abbreviation A for any acid and the hydrogen or the proton attached to it.
Great. So the abbreviation is here's your acidic proton. This is the one that's going to get released. And then this actually is not acid. It stands for anion. Because over here, you see your anion. Anion is a negatively charged ion. Most of the time, it's negatively charged. So you release an H plus from this compound. Whatever that A was, that A in this case was a phenyl ring. That's going to get released. And then you have your H plus and that, and they're separate. So this is kind of a generalized way of saying there's something, and it lost an H plus. So then our generic description for Ka is going to be a concentration of H plus ions, or hydronium, if we use more appropriate terms, whatever the concentration of that anion is over the concentration of that acid together. So I want us to start to think about if something is more or less likely to donate that proton, what does that mean about that anion? What does that tell us about the anion itself? So we're going to talk real briefly about strong acids. And actually, let's go back. And I want you to have a discussion real quick about that top point there. What does it mean? What can you learn about the attraction between the anion and an H plus by looking at the Ka value? Can you tell about the attraction between those? Or maybe you can think about, what can you tell about how stable they are together versus apart? Think about that versus the strength of the acid. Go ahead and take a minute and try to contextualize the attraction between these two, or the stability of it together. All right, I heard some really good conversation. I saw some hand movements and things. Someone willing to share their discussion that they had about the strength of the acid versus the attraction between those two things. Ruby, you raise your hand?
Oh, yeah, sure. I think that if the acid is stronger, since it dissociates more, then there's less affinity between the H plus and the A minus.
What do you guys think about that?
Yes.
Love, did you want to add something to that?
I was basically saying the same thing. I said the attraction, the smaller the Ka, the stronger the attraction between the acidic proton and the anion. So that's fine.
So it sounds really intuitive, but it's hard to wrap your head around. But if you have a carbon-hydrogen bond, those things are really attracted to each other, right? They form a covalent bond, it's nonpolar. It's really hard to get this to separate. That means if you were able to do this, how quickly do you think those two things are going to come back together? Super quick. What does that tell you about how attracted they are? Very attracted to each other. If, on the other hand, you have perchlorate and H+, and those things separate, how strong do you think the attraction is to pull those back together? So what I want you thinking about is stability of them together versus stability of them apart, which tells you about attraction between the two. These two are very stable apart. Perchloric acid is one of our 6 strong acids. Why? Why is it that perchlorate is stable, not with that H+, but the carbon is not? What feature does perchlorate have that a carbon does not typically have? Has double bonds. And what does that allow us to do? What's the word we're looking for? Resonance. That negative charge is actually distributed amongst all 4 of those oxygens. So you could draw out 4 resonance structures. Where that negative charge is at all 4, and it's an average of all 4 of those. So the more evenly you can distribute that negative charge amongst other places, the more muted that negative charge is, the more stable that ion is by itself without pulling the H+ back to it. What's the term that we use to describe how good something is or how strong of an attraction something has to an H+? What do you call something that accepts an H+? Base. So is this a good base?
No.
Alright, and so I want us thinking about what does the basic strength mean about its ability to separate? What does that mean about the strength of the acid? And we're going to talk about conjugate acid bases here in 1 second. So let's talk about strong acids on the other, on that end of the spectrum for 1 second. So perchloric acid is a strong acid. And what we're going to say is that means 100% dissociation. Well, realistically, it's 95% or greater. What does that mean our K values are? If we have 95% or greater dissociation, bigger than 1, 10 to the 5th sometimes, 100 to a billion, right? We can have different Kas. But you guys are familiar with complete dissociation from like salts, right? Sodium chloride goes into water, separates completely. And so we have anything greater than 95%. And notice, going back to, I think it was Matt's point about the arrow, if we're actually drawing the equilibrium arrow for a strong acid, it's probably more accurate to use a full-headed arrow because there's so little of these that combine and go back. What does that tell you about chloride's strength as a base? Is chloride a strong base? Is it a base at all?
No.
It's a terrible base. So bad of a base that if you put chloride, sodium chloride in water, you're not going to have any basic strength of that at all. Nitric acid is one of our other strong acids. Is nitrate a good base? So we can kind of look at all of our strong acids and get some sense for what that means about the properties of the conjugate base that forms from a strong acid. And I think that's actually what we're going to talk about next. Just about. So which of these two does the anion have more attraction to the proton? And I want you to answer this question at least 2 different ways to justify your answer. Once you've answered the question, taken a guess, discuss with your neighbor, come up with at least 2 ways to justify why you picked the one you did. Is that left over from the top?
But once it goes out, it gets but it's just a very strong.
Then you have, I didn't give you K value, but you know which ones are strong. That's one indication, yes. All right. Can I hear a single answer from a couple different people? I think we can get 2 or 3 at least reasons why. Colin?
Weak acid is going to be more likely to come together, meaning that both the proton and the anion are more likely to reform, so they're more attracted to each other.
Okay, so just by the definition of a weak acid, we know that these are less stable apart. The Ka value is going to be smaller. So that means you're going to find more of them on the left side, which means that this is more attracted to its partner than nitrate is attracted to pull that proton off. Okay, what's another reason? Something else we can look at. Moed.
So this may be a stretch, but if you look at A and you look at the Ka arrow, kind of just indicates that you're only making products.
Not a stretch.
And in B, you have it at equilibrium, so that indicates while you're making products, those products are being turned back into reactants, which indicates that there's a strong attraction between the hydrogen and the rest of the...
Great. So just the arrow alone indicates that this reaction really doesn't have any of this that comes back together. Versus the equilibrium arrow says, well, it goes in both directions. And if we're going to be honest, that equilibrium constant is pretty small, 10 to the negative 8 or 10 to the negative... I can't remember what the equilibrium constant is. It's less than 1. So we'd probably actually draw that equilibrium set of arrows like that. We would show that the reaction lies to the left, because it's a weak acid. All right, so we're going to talk a little bit about the strength of a base. And I want to throw one really specific statement in here. So far, I've said, what is the attraction between a conjugate base and H3O plus or H plus? That's actually not how we define the strength of a base, or Kb. We actually say, if we took this thing, this conjugate base, and we put that in water, how likely is that to pull a proton, not from H3O plus, but from water? You see the little difference there? It's not literally the reverse reaction. It is taking this product and saying, if it were to pull a proton from water and remake that acid, how likely is that to happen? It's a little bit different. Same principles are still going to apply. And so we're going to refer to that strength of how likely that reaction is to proceed as our equilibrium constant for the base, or Kb. Josh, you have a question? All right, so let's think about those two definitions. We just said, how likely is something to give up a proton to water is Ka. And on the other side, that thing that gave up a proton, how likely is that to pull a proton from water? That's Kb. I hope you guys noticed that the time factor between those two is water. How likely is it to pull a proton from water or give a proton to water? So I'm going to show you how those two values fit together, and hopefully you'll have one of those aha moments where some of the numbers start to make more sense. So is this describing Ka or Kb? The compound is donating a proton to water. Water ends up with an extra proton. And in the end, we have a conjugate base. That means it differs by 1 proton. It's now the conjugate base of a weak acid. We know it's a weak acid because we have equilibrium arrow. So this is Ka, right?
It didn't take it from water. It gave it the water.
gave it to water. Did I say it the other way around?
No, you were saying earlier though, that's what makes a base though.
Yep.
Yeah.
So then, let's take a look at this. Are we describing Ka or Kb here? How is that anion? And notice here that I use the generic A minus, but this is the same A minus as this A minus. And for this particular part of the class, it's really important that we say that that's the same anion. So it's acetate, it's acetate. We're going to have a conjugate acid-base pair where they only differ by one proton, but the rest of the molecule is the same. So then we can go ahead and write out Kb. I want you guys to multiply Ka times Kb. What do you guys get? You take all this, multiply it by all this, what do we get? Lots of stuff cancels out. Because the anion is the same, if it was a different anion, it wouldn't work. Can you guys see what happens? All right. And that is Kw. I'll tell you what Kw is in 1 second, if you guys aren't already familiar with it. All right, but this is a pretty big take-home, and for the most part, if we know, here's the philosophical take-home from this. If we know how strong of an acid the acid is, we can tell how strong the conjugate base is. Remember we just said that if we have nitric acid, it has a really, really big Ka, so that means the Kb is really small. It's a shitty base. If we have something that's an OK, it's a weak acid, then it's going to be a weak base, because these two multiply together to give you 1 times 10 to the negative 14, which is Kw. All right, so just to make sure we're on the same terminology, a conjugate acid base, this is in activity 42. If you haven't done that already, this is going to be important to work through, is the same compound without and with a proton. That's the only difference. If we have a 2-proton difference, they're not related as a conjugate acid-base pair. In that last slide, remember I said A minus has to be A minus no matter what. It can't be something different. So in this case, we have the acid and the base and the conjugate acid-base pair. And you can look at it the other way around. You can describe it by Kb. How is this able to pull a proton from water? Describes that. Still have 1 minute. So, the last thing that I want us to look at, what does that mean? When I told Tyler earlier, there actually is a non-zero concentration of H+ ions in solution. If you zoom way in with a magic school bus and you see water, this is what it looks like, right? Water molecule, water molecule, water molecule, water molecule, and all of these hydrogen bonds between them. But every once in a while, you have 2 water molecules that transfer a proton. This water acted as a base, it stole the proton. This one acted as the acid and donated the proton. Do you think that happens a lot? It happens a lot as all the time, because we have so many water molecules, but it doesn't happen as a large percentage of them. If we describe that equilibrium constant, 1 times 10 to the negative 14. So that means 1 in every billion or so water molecules is found separate. No, it's actually million billion. And that's kind of where these 2 concentrations come from. Last thing is pH. We took the negative log of Ka times Kb equals Kw. That's where you get this. 14 equals pH plus pOH. All right, we're going to use this on Wednesday. I'm going to build up a pre-class quiz because I don't think I have one for Wednesday yet. And it's going to be about relating Ka and Kb together. Do I have one? And if you haven't completed activities 42 and 43 and you want to turn them in for credit, I highly advise you do them. Turn them in by tomorrow at 5 in my mailbox in the chemistry department. It's on the 4th floor. And I will accept them for full credit.